The number is 10 centimeters. That is how far the Pacific Plate moves every year. 10 centimeters, roughly the width of your hand. For most of human history, geologists call this proof of stability, a slow, predictable, eternal foundation beneath the largest ocean on Earth. They were wrong, not about the speed, about what that speed, sustained over 30 million years, has done to the plate itself. The Pacific Plate, the largest tectonic structure on the planet, covering 1/5 of Earth's entire surface, is fracturing. Not in the future, not in geological projections. Now, and the evidence has been accumulating in the data for 2 decades, while the official geological models refuse to catch up. Subscribe right now. The next 20 minutes will connect dots you didn't know existed. You'll rewatch this. Don't miss what's coming. For most of the 20th century, the Pacific Plate was the centerpiece of a scientific story about order. Plate tectonics, the theory that Earth's crust moves in large cordon slabs, was one of the great intellectual achievements of the 1960s. If you attended school during that era, you encountered a model built on clarity. Here are the plates. Here are their edges. Here is where the earthquakes happen. The ring of fire marked the border. Everything else was settled ground. What the instruments of the last 20 years have found does not fit that model. The geological anomaly is not confined to the ring of fire's perimeter. It is distributed across the plate's interior, in zones that were never supposed to generate any signal at all. We are going to walk through exactly how that discovery unfolded, from the first anomalous readings on the ocean floor, through the physical evidence that confirmed active fracturing, to what that process means for the surface of the planet we live on. The Pacific Plate is not a single rigid slab. It is already fragmenting into a mosaic of separate microplates, and seismic tomography data from the past 2 decades shows this process is accelerating, not stabilizing. That statement needs a moment before you continue. The largest tectonic structure on Earth, a plate that spans from the coast of Japan to the coast of California, from Alaska to the southern rim of the Pacific, is not holding together the way the models said it would. Seismic tomography works roughly like a medical CT scan, but uses earthquake waves instead of X-rays to map the interior of the Earth. What it has revealed are stress fractures propagating through the plate's interior, not at the edges where tectonic friction was expected, through the middle. The textbook version was clear. The Pacific Plate is old, roughly 180 million years in its most ancient sections, and age, in geological terms, meant density and rigidity. Old oceanic crust sinks. It does not shatter. The expectation was that stress would accumulate at the subduction zones, the margins where the plate dives beneath the continents, and release there. As earthquakes and volcanic eruptions along the Ring of Fire's perimeter, that was where the geology was supposed to happen. Consider what that means. Researchers analyzing data from the Global Seismograph Network, a system of sensors deployed across the ocean floor and on islands throughout the Pacific, began noticing something the models had not anticipated. Seismic wave velocities through sections of the plate's interior were inconsistent. In a truly rigid monolith, those waves travel at predictable speeds. When they slow down or change direction, it indicates changes in material density, the signature of rock under stress, rock that is no longer behaving as a single coherent unit. The answer turned out to be tectonic fractures propagating through the lower portions of the lithosphere, the rigid outer shell of the Earth that includes both the crust and the upper mantle beneath it. Zones where the plate is, in the precise technical sense, separating. The irony here is that this was not discovered through any dramatic geological event. It emerged through the quiet accumulation of data that contradicted the accepted model, slowly enough that the contradiction could be set aside. 4 years. Stop and translate that into physical reality. The floor of the Pacific Ocean is coming apart in a process that began long before any instrument existed to detect it. And we only have evidence of it now because our sensors finally became sensitive enough to register what the rock has been signaling for decades. That discovery raised a question the models were not equipped to answer. If the fractures are interior, what is driving them? 10 centimeters per year sounds insignificant. Translate that into the mass of the Pacific Plate, roughly 1/5 of Earth's entire surface, and you are describing a collision force that has been building for 30 million years. The western edge of the plate is subducting beneath Asia and Oceania at some of the fastest rates measured anywhere on Earth. In the Tonga Trench, the plate descends at nearly 24 centimeters per year, faster than your fingernails grow, which is not a reassuring comparison when the object in question weighs several quintillion tons. That leading edge, grinding and diving beneath the continental margins, generates the most seismically active corridor on the planet, the Ring of Fire, a nearly continuous chain of volcanoes and earthquake zones encircling the Pacific stretches. Roughly 40,000 kilometers, approximately the full circumference of the Earth. For decades, the Ring of Fire was understood as proof that the plate was functioning normally. Stress in, tsunamis and eruptions out, equilibrium maintained at the margins. What troubled geologists was what was happening away from those margins entirely. In the 1990s, oceanographic surveys of the Tuamotu Archipelago, a chain of atolls in the central South Pacific, roughly midway between Australia and South America, began returning anomalous heat flow measurements from the ocean floor. These figures exceeded what the models predicted for crust of that age by a margin that could not be explained by measurement error. Old crust runs cold. The thermal energy from its formation should have dissipated over millions of years. But these readings suggested something beneath the Tuamotu region was significantly warmer than it had any right to be. Think about that for a moment. Then came the Manihiki Plateau. The Manihiki Plateau is a large underwater highland in the central Pacific, formed roughly 120 million years ago during a period of massive volcanic activity. By every conventional assessment, it was geologically inert. A relic of a much earlier episode of Earth history, a structure the planet had finished with long ago, except that it wasn't finished. Bathymetric surveys, three-dimensional maps of the ocean floor built from sonar data, revealed deformation patterns in the Manihiki Plateau that were inconsistent with a stable and seamed formation. The seafloor topography showed evidence of relatively recent vertical displacement, not the slow, uniform sinking expected of cooling oceanic crust, but irregular shifts, blocks of the ocean floor moving relative to each other in ways that indicated active stress in the underlying lithosphere. The word recent in geological time requires translation. It does not mean last year. It means within the past several 100,000 years, which, on the scale of a 120-million-year-old formation, is approximately yesterday. These were not zones where the models predicted activity. The Ring of Fire was behaving as expected. The interior was not supposed to be generating anomalies. And yet the Tuamotu heat readings and the Manihiki deformation data were converging on the same conclusion. Stress inside the Pacific Plate was not being fully discharged at the subduction zones. It was accumulating in the interior. It was finding other paths. The physical evidence on the ocean floor was about to make that finding considerably harder to set aside. Researchers listening to the ocean floor have recorded low-frequency acoustic signatures. Not earthquakes, not volcanic eruptions, but the sound of rock under stress that hasn't moved in millions of years, beginning to move. The instruments that captured these signals are hydroacoustic sensors originally deployed during the Cold War to detect submarine activity and nuclear after the Comprehensive Nuclear Test-Ban Treaty of 1996. That monitoring network was repurposed for scientific observation. What it began recording in the years that followed was not what the researchers expected. Acoustic events originating from the interior of the plate, not at the margins, not at known fault lines, but from zones that had no reason to produce any seismic signal at all. That is the first category of physical evidence. The second is chemical. Oceanographic sampling in the Central Pacific has documented elevated concentrations of methane and carbon dioxide rising through the ocean floor in areas remote from any known hydrothermal vent system. Methane and CO2 are both products of geological processes in the mantle. They migrate upward through fractures in the crust. Finding them in elevated concentrations deep in the ocean, far from the continental margins, is a chemical signature of fracturing. The rock is cracked. The gas is escaping through the cracks. The third category of evidence is the most direct. In several locations across the Central Pacific, including zones near the Manihiki Plateau, deep-sea sampling has recovered visually fresh basaltno sediment cover. Clean, dark rock, free of the manganese crust that accumulates on oceanic surfaces over hundreds of thousands of years. Fresh basalt on the ocean floor means recent tectonic or volcanic activity, recent enough that the geological record-keeping system of sedimentation has not had time to archive it. This is not a theory. This is physical sample evidence, documented in peer-reviewed research, sitting in repositories that have been available to the scientific community for years. Now, consider the mechanism driving all of it. The base of the Pacific Plate is in contact with the mantle, the layer of semi-molten rock beneath the rigid lithe, circulating at temperatures around 1,200 degrees Celsius. Over millions of years, the plate has been gradually thinning in certain regions through a process called thermal erosion, where mantle heat effectively dissolves the underside of the crust from below. In areas where the lithosphere has thinned sufficiently, the plate's mechanical resistance, its capacity to remain rigid under pressure, is compromised. At the same time, the plate is under compression from multiple directions. The subducting edges are pulling it downward and forward. The continents on the western margin are pushing back, and the weight of the ocean water above averaging nearly 4 kilometers of depth across the Pacific Basin and reaching nearly 11 kilometers at the Mariana Trench. The deepest point on Earth's surface presses down on a structure whose base is being dissolved by heat from below. The plate is simultaneously being pulled, compressed, and thermally weakened from underneath. The process operates on timescales of hundreds of thousands of years. From within any single human lifetime, it is invisible. But the acoustic data, the chemical sampling, and the fresh basalt recovered from the ocean floor all point to the same conclusion. The rate of that process has measurably increased. The fracturing is not theoretical. It is active. It is occurring now across multiple interior zones. Simultaneously, the most unsettling part is still ahead. When the floor of the Pacific shifts, the ocean above it shifts with it, and the currents that regulate weather patterns across the entire northern hemisphere are not immune to what happens 3 miles below. The connection between ocean floor topography and surface circulation is not speculative. It is one of the most established areas of physical oceanography. Underwater ridges, plateaus, and trenches function as channels and barriers that direct deep-water currents, the thermaline circulation system that moves cold, dense water from polar regions toward the equator and back. This circulation is what stabilizes climate patterns across the Pacific Basin and through the atmosphere, far beyond Italiano. If interior fracturing in the Pacific Plate alters the topography of the ocean floor through vertical displacement, new fracture zones, or shifts in the distribution of hydrothermal heat, it alters the channels through which those currents move. The effect is not immediate. It develops over centuries to millennia, but it is not reversible on any timescale relevant to human civilization. The more immediate concern is seismic. Interior plate fracturing produces earthquakes that differ from subduction zone events in one critical respect. The source geometry is less predictable. Coastal early warning systems for tsunamis are calibrated to known fault geometries along established subduction boundaries. A major earthquake generated by an interior fracture event in a zone currently classified as low risk would test those systems against a scenario they were not designed to handle. There are approximately 1.2 billion people living in Pacific coastal zones today. The infrastructure supporting those populations, port facilities, undersea communication cables, shipping lanes carrying a significant share of global trade, is engineered around a geological model that the data is now actively The climate change dimension is worth naming precisely. It is not that interior plate fracturing causes climate change in the conventional atmospheric sense. It is that the processes interact in ways that amplify each other. Methane release through ocean floor fractures is a potent greenhouse gas. Disruptions to deep water circulation redistribute how heat moves through the atmosphere. The ocean floor is not a passive substrate beneath the climate system. It is part of the system, and it is not behaving as predicted. And that system has a history that gives this moment a recognizable shape. 10,000 years ago, the Earth was completing a transformation you likely encountered in school as the end of the Ice Age. Sea levels rose by roughly 120 meters as the ice sheets collapsed. Coastlines that had been inhabited for millennia were submerged in geological time. The record from that period shows elevated seismic activity across multiple tectonic regions, a documented response to the redistribution of enormous mass as ice sheets melted and ocean basins refilled. The lithospheric plate movement we are observing in the Pacific today has a structural precedent in that event. The mechanism is different. Not ice loading and unloading, but thermal erosion and interior stress accumulation. But the pattern is recognizable. A geological system in approximate equilibrium begins a transition. The transition manifests as increased interior activity across a wide area before it produces any surface event dramatic enough to force a revision of the prevailing model. What geologists are describing when they discuss the current state of the Pacific Plate is not a catastrophe in progress. The operating word is transition. Transitions in geological systems are not sudden, but they are not gradual in the way everyday experience defines gradual. They involve extended periods of relative quiescence, centuries, punctuated by concentrated episodes of activity whose distribution across time is not uniform and not predictable from a seismic record as short as the one we have. 100 years of instrumented observation is not sufficient to establish a reliable baseline for a process operating on timescales of hundreds of thousands of years. What we do have is instrumentation that previous generations of geologists could not have imagined. The hydroacoustic network, deep-sea sampling programs, satellite-based geodesy measuring millimeter-scale surface deformation, these tools did not exist in 1965. When plate tectonics was being assembled into a coherent scientific theory, the model was built with the instruments available at the time. The instruments have improved substantially. The model is now being forced to catch up with the evidence those instruments are producing. That is not a failure of science. It is science functioning exactly as it is supposed to, revising itself when the data demands it. The harder question is whether the systems we have built on the surface of the planet are structured to revise themselves with the same discipline. The Pacific Plate was never a foundation. It was always a process, a structure in motion, under stress, responding to forces operating on timescales so vast they register as stillness from the perspective of a human lifetime. What changed is not the plate. What changed is our instruments, and through them, our ability to see what was always happening. There is something worth sitting with in that. For decades, the stability of the ocean floor was not just a geological assumption, it was a civilizational one. We built ports, cities, and the infrastructure of global commerce on the implicit understanding that the ground beneath the sea had finished its major transformations. That confidence was not unreasonable. It was simply premature. The ocean floor is rewriting itself right now. Tonight, in complete silence, 3 miles below the ships crossing it. That process was underway long before the first city was built on the Pacific Rim, and it will continue long after the last one. The ground beneath us was never as still as we believed. The next mystery is already waiting. Subscribe now and be there when we open it.